Hi, very good morning to all of you. The last class we discussed about the hysteresis loop and their properties. Today we are going to discuss about the minor hysteresis loop and recoil line. Minor hysteresis loop and recoil line. So we have the different types of permanent magnet materials. We studied in the last class. So we have four types of permanent magnet material. The first one is Alnico. Alnico permanent magnet material with the different grades. Alnico is alloy of aluminum, nickel and cobalt. So the main application of Alnico magnet is radar systems and motor applications, generator applications. We have a number of applications suitable for Alnico magnet. The second magnet is called a ceramic magnet. Second magnet is called as ceramic magnet. So this magnet is suitable for computer hard disk drives and microphones, mobile phones, and also suitable for various commercial applications. So next magnet is called as SMCO, samarium cobalt magnet. So this is very popular magnet for magnetic motors and generators. Magnetic motor and generators. The value of retentive flux density BR and coercive force HC both are higher values. So next magnet is called as NdFeB magnet. NdFeB magnet alloy of neodymium, iron and borons. So this magnet is the strongest magnetic property among these magnets. So main application of this magnet is toys and also suitable for magnetic motors and generators. So among these all magnetic materials, NdFeB magnet and SMCO magnet mostly suitable for magnetic generator and motors. So the last class we studied the hysteresis loop of magnetic materials and the property. What is a hysteresis loop? It is the working in the second quadrant of the hysteresis curve. So we have here we have the XY plane. In this XY plane, this is a magnetizing force. This is a flux density B. It is the first quadrant of BH loop. It is the second quadrant of BH loop. It is the third quadrant. It is a fourth quadrant of BH loop. Okay. So here minus B, here minus H. Okay. So this first quadrant is a magnetizing. Second quadrant is a demagnetizing. First quadrant is a magnetizing. Second quadrant is demagnetizing. The third quadrant is magnetizing in the reverse direction. Fourth quadrant is demagnetizing in the reverse direction. So we have the fourth quadrant. First quadrant is magnetizing, demagnetizing, magnetizing in the reverse direction, demagnetizing in the reverse direction. So these all four magnet material work on the second quadrant of BH loop. So operate is the second quadrant. So the quality of the magnetic material is characterized by three parameters. The one parameter is called as BR. BR means retentive force or retentive flux density. BR means retentive force. Second one is HC, coercive force. Coercive force. And another one parameter is called as BH maximum product. So these three parameters decide the quality of the magnetic materials. So this is a hysteresis loop of permanent magnetic materials. So the last class I also studied. This is very, very important. So we have. So first let's consider the closed ring of magnetic material. This is a closed ring of magnetic material. This is a closed ring of magnetic material. In that, wound uniformly winding and then passing the electric current through the winding to the magnetic ring. What happened at the initial position? The current I equal to 0. At initial position, the input current I is 0. Now, the corresponding point is called as O. The corresponding point is called, this is a corresponding point because in this condition, the both B and H equal to 0. Because there is no magnetic force and magnetizing flux density set up with the magnetic materials. So the corresponding point is called as, this is a corresponding point. Now the current is increased from 0 to certain value. The both B and H set up in the magnetic material, it will follow the path O to A. It will follow the path O to A. Okay. At a certain value of the current I, that both B and H reach the saturating value or reach the saturating point. Okay. So this point is called as A. This point is called as A. This point is called as A. Now corresponding point on x-axis is called as maximum magnetizing force. The corresponding point on the y-axis is called as maximum flux density of the magnetic materials. Now the applied current to the closed ring specimen is maximum value. Now we have to reduce from maximum value to 0. Now the current is decreasing from the saturating point. This means the current is decreasing from A. So now what happens? See, this line do not follow the previous path. It will follow the some other path, like path is A to B. A to B. The path is A to B. This point is called as BR. This point is called as BR. The point BR, what is the value of the current? The current is at point BR, the current I equal to 0. The current I equal to 0 and H also 0. Because see here, H equal to 0 in this point, the current also 0 in this point. So the path is now this point. O to B. This point is called as, so this period is called as residual magnetism or retentive flux density of the magnetic materials. Now we want to reduce flux density to 0. What we do? We make this H is to be reverse direction by changing the direction of current. By changing the direction of current, so that by changing the direction of current, so that it will fall like this. The path is B to C. The path is B to C. At this point C, the value of the BR equal to 0. At the value of the BR equal to 0, and H equal to negative value of this HC. H is equal to negative value. This is because this point is called the coercive force. But the coercive force is the negative value. So the magnetic force in the negative direction. So further increasing current, what happened? See here, this is coming in the point C enter to the magnetizes in the reverse direction, like that entering point. The following path is C2 and D. At this point D, the B and H both are saturated in the reverse direction. Again we can follow the procedure, same procedure. So we reduce the current. We reduce the current like this. So it follows this point. This is a B or in the negative direction or reverse direction. So further, this curve following path E to F under magnetization like this point F to A. So this is a complete hysteresis loop of permanent magnetic material. Now the initially starting point at current I equal to 0, point is O. Next the current is maximum value point A, and again reduce the current is 0, that is called point B. Next current is reverse direction, the point C and point D. Next E, F, A. So this is one cycle of hysteresis loop. But while considering practical application, we are not consider this type of magnetic loop or hysteresis loop for particular applications. So we are going for practical application, we consider minor hysteresis loop and recoil line. So while designing of many applications or practical applications like applications such as motor, generator, for application we not consider this BH loop. We consider only minor hysteresis loop and recoil lines. See here, this is for demagnetization curve in the second quadrant. So this is for the minor loop. This is called as minor loop. This is called as minor loop. This is for recoil line. This is for recoil line. So we have the four types of magnetic material we already studied. These are the characteristics of for magnetic material. The first one is Orlico with 7. This is the maximum value of the BR. Maximum value of BR and minimum value of the HC. Minimum value of the HC. Similarly, ceramic magnet. This is ceramic magnet. So it is lower value of the BR and relatively higher value of the HC. Similarly, another magnet is called as SMCO magnet and neodymium iron and boron magnetic material. These two material having similar value of BR and HC. Okay, this is a demagnetization curve in the second quadrant. Now, this is an actual BH loop. See here, this is actual BH loop in the second quadrant. This is actual BH loop in the second quadrant. How will create this loop? That is very, very important. Based on this loop only we will apply for particular application for all these permanent magnet materials. Okay, so here the minor loop is a part of the major loop. Minor loop is a part of the major loop. So this is a major loop. This is your major loop. Okay, major hysteresis loop. But this is a minor loop. So it is a part of the major loop. And another one. So minor loop is a closed loop. It does not reach the saturating point value. So see here, the previous case, see here, this point is saturating. This is a major hysteresis loop. The major hysteresis reaches saturating point, certain value of the current, both forward direction and both reverse direction. But see here, so the minor loop does not reach the saturating point. Does not reach the saturating point or saturating value. So next, how to design? The design of electric apparatus using permanent magnet material is generally based on the recoil line rather than rather than the original demagnetization curve. Original demagnetization. What is the origin? Where is the original demagnetization curve? This is the original demagnetization curve. Nickel, ceramic, sumerian cobalt, NdFeB. This is the original demagnetization curve. But while considering practical application, we consider only minor hysteresis loop. Minor hysteresis loop. Okay, so we'll see how we'll generate or how we'll obtain hysteresis loop, minor hysteresis loop and recoil line now. So this, see here, we already discussed in the previous section. The current I equal to 0, both B and H equal to 0. So there is no magnetic flux density and magnetizing force set up in the magnetic material. So this point is called as 0. Now the current is increased from 0 to certain value. Now B and H set up in the magnetic material, it is increasing linearly like this. At a certain point, at its saturating value, the point is called as A. In this point, value of the flux density is called as B max. The corresponding point on the x-axis is called H max, magnetizing force. Okay. Now current is, you assume that now current is the maximum, well, I is the maximum. The current is decreased from saturating point to certain value. This curve meet at point B on the y-axis. The curve meet at point B on the y-axis. At this point is in this point the value of the H equal to 0. The value of the H equal to 0. The BR, the 0 to O2 BR equal to residual flux density or retentive flux density. Now what happens? See here. This is very important. At this point, what is the value of the current? In this point, the current I equal to 0. In this point, current I equal to 0, H equal to 0, H equal to 0. So I also 0, H also 0. So at this point, we completely remove the magnetizing force from the magnetic material, so that H equal to 0. So we only present flux density. Okay, so that flux density is called as residual flux magnetism or retentive flux density of the magnetic materials. Now see, the current is increases in this reverse direction current is increased reverse direction. See, current is increasing from 0 to maximum value in the reverse direction. The path is following like this. It reached the point C. It reached the point C. The corresponding point is in the y-axis called as minus H1 or minus Hc. So the current is minus I1. The current is minus I1. Okay. Now here very important. How will generate minor hysteresis loop? Minor hysteresis loop. So further increasing current, what happens? See, the further increasing current reverse direction. This point try to move point D. Suppose we decrease the current back to the 0. So in this we assume that we are decreasing current from 0 to maximum value to 0. So this curve, it is not following this path. Actually it follows this path, but it does not follow this path. We'll find another loop is called as, like this is going. So this loop is called as minor hysteresis loop. Okay, while decreasing current from the point C to B, the line should follow C to B, path C to B, but it does not follow that path. It will follow like this and generate on closed loop. So this loop is called as minor hysteresis loop. We draw the straight line on the one loop is called as, on the line, we draw the one straight line on the loop is called as recoil line. This line is called as recoil line. This loop is called as minor minor hysteresis loop. Minor hysteresis loop. So next one, see here, same I explain here. If the current is reduced to 0, in this point I equal to 0, now current is increased in the reverse direction. The current is increased, reduced to 0. See here at this point, now this point, this is now corresponding point. Now current is reduced to 0. See here, the path does not normally move to the loop towards the point B. Actually it will move. It will move from C to B. But so instead of it start to trace out minor hysteresis loop. See here, it will follow this path. This path. So this loop is called as minor hysteresis loop. Minor hysteresis loop. This loop is called as minor hysteresis loop. Okay, so we draw this one straight line on the loop is called as recoil line. The line is called as recoil line. Okay, so next one is, as the current varies from 0 to I1, we discussed the minor hysteresis loop may usually replaced with a little bit error. That straight line, that line is called as recoil line. That line is called as recoil line. So this line has slope is called as recoil permeability, which is approximately same that of the original BH curve. Okay, so here, so minor hysteresis loop and major hysteresis loop both are equal value. B equal to BR at H equal to 0. So this is very important while considering practical application. So based on the minor hysteresis loop only, we decide the characteristics of the magnetic motors and the generator line applications. So what are the applications of permanent magnet materials? So first one is a ferrite magnet or ceramic magnet. The ferrite magnet materials mainly used in magnetic motors and loudspeakers and vehicle magnetic application are and also suitable for many commercial purpose or many commercial application, loudspeaker and microphone, headphones. So n number of applications. And the next one is smoothing cobalt. It is also called as SMCO. SMCO is mainly suitable for electric motor application, medical applications, and marine and aerospace application, etc. Next one is a neodymium magnet. So neodymium magnet also called as NdFeB. So neodymium, iron and boron. Neodymium, iron and boron. So this type of material used in electric car, motor applications, medical applications, toys applications, generator application. So we should be because it is the highest magnetic strength of magnetic among the magnetic material. Okay, so next one is called as oligomagnet. Oligomagnet having higher value of Br and lower value of H. HC. So that it is mainly suitable for MRI scan, radar communications, electron tube for communication purpose, for generating frequency. All are the main applications of oligomagnets. Next one, summary. Now we will discuss summary of the today class. First one, we discuss the different types of magnetic material. Magnetic materials. Second one, we discussed Major hysteresis loop. Third one is minor hysteresis loop. In the minor hysteresis loop, we also discussed how to obtain minor loop and recoil line. Okay, so for practical application, based on this practical applications of minor loop. So next we discussed the applications of permanent magnet material. Applications of permanent magnet materials. So we have four types of permanent magnet material. Alnico. Second one is ceramic. Third one is SMCO. And the fourth one is neodymium, iron, and boron. So Alnico, very important application: radar, MRI scan. Second one, ceramic, computer hardware or computer hard disk drives, loudspeaker, and many more etc. Many more applications. And SMCO, motors and generators, aerospace, and marine applications. Next one, magnetic material is called as NdFeB. So this is the very strongest magnetic material among these. Is suitable for motor and the generator, toys, etc. So these are all the summary of this today class. So today class we discussed what is a major hysteresis loop, what is a minor hysteresis loop, what is the use of minor hysteresis loop, what is a recoil line, and also we discussed the different types of applications of permanent magnet material. In the next class, we will discuss how to handle the permanent magnet materials, and also we discussed cubic temperature effect on permanent magnet materials, and also we discussed properties of permanent magnet materials. Thank you.